Okay, in this video we are going to do some of the problems on pages 9 and then 10 of Notes 2. So let's kind of dig right in. So the function that we're dealing with is f of x is cosine of x. And the problem tells us to write the Taylor polynomial centered at x equals 0 having three non-zero terms. So I actually, later on you're going to memorize these. So I have this memorized, so I'm just going to write it down. So p of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So that's my polynomial. So if I want to approximate cosine of 0.7, I just plug 0.7 into that. So the cosine of 0.7 is approximately p of 0.7, which is, I'm writing exactly. I don't remember if that's exact or not. I don't really see how it could be. But anyway, to 3 decimal points, we'll go with that. Now what I want to do is I want to try to figure out the possible error involved. And this is where things, for some people, get complicated. So I need to understand how I got that 4th degree polynomial there, the 3 non-zero terms. So what I'm going to do is I'm going to reconstruct a table. So n, the nth derivative, and then the nth derivative at 0. So you can see, so I'm going to list all my derivatives here. So I get to this. Okay, so I needed up to that derivative to write the polynomial, which means that I should need one more to get the error. So I'm going to use the 5th derivative to determine the possible error. So here are the values. So you can see why I need the first 4 derivatives to get 3 non-zero terms because of those zeros, and it just keeps alternating. So let's do this. So I need to find m. I used the 4th derivative to write the polynomial. So what I need is my n plus first derivative will be the 5th derivative. Okay, so m is the maximum of the absolute value of the 5th derivative on the interval from 0 to 0.7. Okay, 0 because it's center, 0.7 because that's where I'm approximating the function. So if you look at m, the absolute value of the absolute value of the absolute value of negative sine of x is just sine of x, and that's always less than or equal to 1. So that's a super convenient value. So I'm actually just going to use that. So I put a bound on the possible value of m. So m has to be less than or equal to 1. 1 is a very convenient number, so that's what I'm going to go with. So now I just set up the error. The absolute value of the error less than or equal to m. The absolute value of 0.7 minus 0 to the 5th over 5 factorial. Which is approximately 0.001401. So that's a very small error. So I can now trap the value of cosine of 0.7. So it's between my estimate minus the error and then my estimate plus the error. And then I use the calculator to just kind of knock these numbers out. So I know that cosine of 0.7 is somewhere between those two numbers. But then you might notice that if I were to evaluate the function, the 5th derivative, at x equals 0, I would get 0. Which means, in some ways, that the 4th degree Taylor polynomial is the same as the 5th degree Taylor polynomial, which means I could argue that I actually used the 5th derivative to write that polynomial, which means I would bounce to the 6th derivative to calculate m. So what I'm going to do is I'm just going to show you what happens if you do that. So I would get a second error. I'm still using 1 for my value of m, except now it's to the 6th power and then over 6 factorial. And since 0.7 is less than 1, that gets smaller, and then I divide by a higher factorial, so it gets smaller still. So this error is approximately really, really small. So basically it's like almost 1/10 of the previous one. So now I can trap cosine between these bounds, and you can see it's going to be a much smaller interval. So using a calculator, I got this. So this is actually, it's a very accurate estimate of the cosine of 0.7. So that's one example. What I'm going to do now is I'm just going to bounce to, this is everything that I did for the next problem on the page. You can pause the video and look at it, and what I'm going to do is I'm going to move on and do the first problem on page 10, which involves the natural log of x. So what I've done is I've moved on to page 10, and I'm doing the first problem. So f of x is the natural log of x, and I want to center that at x equals 1, and I want 4 non-zero terms. So let's make our table. And I need 4 non-zero terms, which means I know that when I plug in 1, that's actually going to cause, do I want 4 non-zero terms? 0, 1, 2, yeah, okay. So I didn't actually do this problem right. So let's just change the problem and do 3 non-zero terms, because I'm not going back and redoing this whole thing. So I'm going to use 3 non-zero terms and do all my work from there. Probably I'll go back and just edit the notes so it says that, so you don't really need to worry about it. But if you look, I get a 0 for the first thing, and then I get 3 non-zero terms, so I'm going to stop there, put my line in my table. So I'm going to end up using the fourth derivative to calculate the error. If I had used the actual 4 non-zero terms, I would have needed the fifth derivative. My estimate would have been more accurate, so good job by me. Okay, so I can write my polynomial. Just following Taylor's theorem. It's the pattern. Make sure you have this memorized. Really not that difficult to remember. So I get this. I'm going to clean that up. And so it's actually a nice polynomial to work with. So I have this. So if I want to approximate f of 1.8, that's going to be approximately p of 1.8, which is exactly, exactly to 4 decimal places, 0.6507. Okay, now I need to find the error. So m is going to be the maximum of the absolute value of negative 6x to the negative fourth on the interval from 1 to 1.8. 1 because that's the center, 1.8 because that's what we plugged into the function. So if I just look at 6x to the negative fourth, I know that's a decreasing function because the numerator stays the same, the denominator gets bigger as x increases. So the maximum must be at the left end point, which is x equals 1. Plug in 1, you get 6. So the actual value of m in this case is 6. I don't need to put a bound on it. So the absolute value of the error, I just plug into my formula, which gives me that, and then use a calculator here. So 4 decimals, or possibly the exact value. It actually might be the exact value in this case. 0.1024. So my estimate minus the error is less than or equal to the actual value is less than or equal to my estimate plus the error. Then if you use a calculator, you can get an interval. So there you go. That's a couple of examples of using Taylor polynomials to approximate, finding an error, finding an interval on which the actual value must fall. And one thing to remember is as you use more and more terms, the error that you're getting will decrease, which means that the more terms you use, kind of the better. So I hope you found this helpful, and good luck.